There are over 8 billion people on Earth, generating endless combinations of behaviors, opinions, and traits. Before you ever write a survey question, you must first navigate the logistical nightmare of finding specific individuals within this global population. You obviously can't interview everyone, so you have to select a tiny fraction of people to represent the whole. But pulling the right voices from a sea of millions without getting lost in the noise is incredibly difficult. If you choose the wrong respondents, your data is compromised from day one. To cut through the chaos and guarantee valid results, researchers rely on a highly structured process known as a sampling blueprint. This blueprint operates like a giant funnel. At the very top is your target population. This is the complete theoretical universe of people relevant to your specific research question, say every registered nurse in the United States. But a theoretical universe doesn't give you phone numbers. You have to narrow it down to a sampling frame. This is a tangible, official list you can actually access, like a national registry of active nursing licenses. Finally, at the very bottom of the funnel, you extract your sample. This is the strictly controlled subset of individuals pulled directly from that list who will actually participate in your study. Here is a visual representation of where this process often breaks down: coverage error. If your sampling frame, the smaller ring here, doesn't properly overlap with your target population, you end up with a massive blind spot. Maybe the registry you used is 5 years out of date, or it excludes nurses working in private practice. If you build your sample from a flawed list, you exclude entire demographics, and any conclusions you draw about the broader population simply collapse. Once researchers establish a solid frame, they face a major fork in the road, deciding exactly how to pull people from that list. This splits into two distinct strategic paths: probability and non-probability sampling. Probability sampling relies entirely on mathematical randomness. If your goal is to take a small sample and confidently apply its findings to the entire national population, you are required to use this approach. Non-probability sampling throws out strict randomness. Researchers take this route when their populations are hidden, or when they need deep exploratory insights into a highly specific group, rather than broad statistical spread. Let's look at the mechanics of probability sampling. The purest form is simple random sampling. Like a lottery, every element in your frame has an exactly equal chance of being selected. If you have a perfectly ordered list, you might use systematic random sampling. You pick a random starting point and then select subjects at a fixed interval, like grabbing every 10th person on the roster. But what if one group is much smaller than the others? Stratified random sampling organizes the population into specific subgroups first, say by income or education level. Then you randomly sample within those boxes to guarantee fair representation. Finally, if you survey a massive, geographically dispersed population, getting a complete list is impossible. Instead, you use cluster sampling, breaking the population into natural geographic chunks, like counties or city blocks, and randomly selecting a few areas to study in full. While they approach the problem differently, all four of these techniques exist to solve specific logistical challenges in the field, all while preserving the mathematical randomness required for solid data. However, perfect sampling frames rarely exist for highly specialized qualitative research. You can't download a registry of undocumented workers or corporate whistleblowers. In these cases, researchers use purposive sampling to deliberately handpick individuals with specific expertise. Or they use snowball sampling, where a few initial, hard-to-find subjects recruit other subjects from their own private networks. Mapping unknown or highly specialized human behaviors requires the precision of a targeted search, making non-probability sampling the only viable tool for these specific discoveries. So you've defined your target, found your frame, and picked your method. There is one final filtration step. How many people do you actually need? This animation shows the golden rule of quantitative statistics, the central limit theorem. Watch what happens as our sample size grows. Once you reach a minimum of 30 subjects, the chaotic data typically stabilizes into a predictable, normal distribution. Qualitative research throws that numerical baseline out the window. Instead, it relies on the concept of theoretical saturation. You don't aim for a fixed number. You simply stop collecting data the moment your interviews stop generating new insights. But reaching that saturation point is unpredictable. You might spend an hour interviewing an expert, only to hit a wall where they stick to rehearsed answers and yield zero usable information. That friction is part of the process. Ultimately, quantitative studies sample to reach numerical stability, while qualitative studies sample until their conceptual map feels complete. This brings us all the way to the bottom of the funnel. You've defined the theoretical universe, extracted a workable frame, chosen a strategic method, and established your required sample size. Executing this blueprint in the real world is always a balancing act. Every decision you make is a forced compromise between your research budget, your timeline, and the precision of your data. A massive spreadsheet of responses might look impressive, but the ultimate conclusions drawn from any study are only as powerful, valid, and truthful as the sampling blueprint used to build it.